Morning, everyone. So this will be our last lesson of new content. This ends us off for Chapter 5. We're going to flesh out a little bit of the concepts that we talked about yesterday. We took a look at enthalpy, sort of the heat change in the reaction. Usually the exothermic direction is more stable. And entropy, which we only spent a half lesson on it. This one here was talking about the disorder, the amount of chaos in the system. The second law of thermodynamics guaranteed me things tend to get more messy. We're always fighting this losing battle. Today we're going to flesh out that very last formula that we derived. We'll talk about this notion of free energy, what it means to be free, and also to sort of make some predictions with which reactions are spontaneous or not. So let me just backtrack just a little bit here. As we were deriving for the entropy side here, we were saying the entropy of the universe is separated between the entropy of the system and the entropy change in the surroundings. Right? So the universe is way too big a place to study. Let's just localize ourselves just looking at the reaction or just looking at the outside. I was mentioning, so second law of thermodynamics says we're fighting this losing battle. The entropy in the universe is always bigger than zero. It's always increasing. We're always getting more messy. We're always getting more chaotic. We use the room as an analogy here. Again, nobody in their sane mind would, I'm going to make my room messy or I'm going to make my house messy today. It just naturally happens. You might, seeing the mess one day, you might be like, okay, fine, I'm ready to clean my room or whatever. We're still fighting this losing battle. Let's say you go to clean your room. You might be able to sort of make a nice pile of your shirts, make a nice pile of your clothes, hang up your scarves, things like that. What we're going to do here, the picture is still very depressing. You can locally, sort of in the small scale, sort of in the system, you can locally gain order. So you can put things back into order. So that actually is a decrease in entropy, right? Decrease chaos. But the second law here still applies, even though you're sort of sweating away and spending a lot of time and energy to sort out your room. What this law here, very depressing, says is somewhere else in the universe, in the amount of time and the heat that you've lost in doing this process, somewhere else in the universe, it's increased chaos more than what you can do. Physicists refer to this as the gradual heat death of the universe. Eventually, because the entropy is always increasing, the energy is never going to compact, it's never going to condense in on itself, and we're just gradually sort of averaging out. Overall, the quantity of energy stays the same, but the quality is steadily being degraded. Just finishing this off here. So somewhere else in the surroundings has become more chaotic. So while your room may look a little bit neater, it's nice, right? It's not a pain to look at anymore, but in you sweating away and spending that time and energy somewhere else, it's more chaotic than what you did. So we're always fighting this bigger than zero or this losing battle. We saw a little bit of hand-wavy math last day, and we had made the derivation. Delta S was hidden in a term here called delta G. We saw that delta G was sort of part enthalpy change. It was a minus T delta S. We saw somewhere along the way we had to do a multiply -1. So that when the second law says this is supposed to be greater than zero, for this free energy change to obey the second law, we actually wanted this one here to be less than zero. And that's where we left off with last day. Today we're really just going to focus on, well, what is the energy argument? Is it endo? Is it exo? How does this term interplay with with the entropy argument, and how does it actually specify this free energy term? So, just a little bit of recap here. We are looking at the spontaneity of the reaction. We're looking at whether reactions occur without any outside influence. This is beyond any activation energy. It's beyond any spark to get the reaction going, which actually determines the rate, which we had assumed in the previous day. What we're going to do in this lesson here is we're going to just ask ourselves, what does nature want to do? We need to factor in both enthalpy and both entropy as argument. They're sort of two halves of the same story. We spent a lot of this chapter focusing 7 different ways of finding delta H. We only had one way of finding S, products minus reactants. If nature had its way, nature tends towards the side that has low enthalpy. So when you plot an energy level diagram here, make sure you label your axes here. If it's exothermic, I would say I would prefer the other side because I'm lower energy. For an exothermic reaction, we expect the heat term to be on the right-hand side. If it were an endothermic reaction, in contrast, H against time or H against reaction, I start low and I end high, I still would favor the lower energy side. Nicely here, C plus heat. I also favor the side that has the heat term. So, one thing here is we say nature likes going low enthalpy. Given a choice, it likes to go to the low energy side. It doesn't always happen though. It prefers the exothermic direction. It prefers to go to the side that has the heat term on it. Entropy, because of the second law, like we just said, the entropy is always increasing in the universe. We're always fighting this losing battle. We're always going to look for the side that has the most moles, the highest number of the most random phase. We had that relative order: solids, liquids or aqueous are somewhere in between, and gases are definitely the most entropic, the most chaotic state. Just some comments here on that second law of thermodynamics. We talked about universe's entropy is always increasing. Free energy is just a nice convenient way. It does look at entropy directly. We see a delta S term directly, but it also tracks some indirect entropy changes in the surroundings by looking at energy. So when we did the derivation with that hand-wavy math towards the end of yesterday's lesson, by using this one formula, I can study both the energy argument and the entropy argument in one and the same formula. Depending on the signs and the sizes of these numbers, I can figure out which ones actually obey the second law and which ones would actually be spontaneous. If I don't obey the second law, the reaction is not going to proceed. I'm going to stay on my side. So this is one last formula that we have. We did call this guy here a Gibbs free energy. Free energy here, it's energy that's available. It's energy that's free. It's energy that you can use. So we're going to use a sort of a battery as an example here. Inside the battery, there's chemicals inside. They're supposed to be reacting, and they're supposed to produce some useful electrical energy out of it. That's the free energy that's available from the battery. When it's under a guy called Gibbs, Gibbs did everything under constant pressure, which is what we're under here. We always have roughly 1 atmosphere of pressure. We're not necessarily going to be in a heavy-duty container that can change the pressure. Under Gibbs conditions, under constant pressure conditions, we want to know how much free energy is available. We had made that derivation last day here. We saw that when the change in Gibbs free energy, when I go from reactants to products, if the change says negative, it's going to be spontaneous. So delta G negative, spontaneous. Delta G positive means non-spontaneous as written. In fact, I don't want to go forwards. It's because the products are so good at coming backwards, that happens spontaneously. There is a crossover value we'll see in today's lesson here. When the delta G value is actually equal to 0, it switches from one to the other. We're going to see on the backside here that it doesn't switch all at once. It doesn't go like spontaneous, 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 and then suddenly switch non-spontaneous. It takes a little while to actually cross over, which will hit something called equilibrium. So let's just work through an example here. I've given you a reaction. This one here, although it's not necessarily a combustion reaction, this one here is written as a reverse of a combustion. And just like we did when we learned those 7 different ways of finding delta H, if this is sort of representing combustion, I don't want to use combustion way to solve it. So technically for this delta H here, we have our 7 methods. We can do calorimetry, we can do bond enthalpy, we can do all that. I already said this one here is like a combustion. I don't want to use combustion. Because I'm not given experimental data, you can't do calorimetry. This one here is a liquid. I can't do bond enthalpy. I'm not given many equations, so don't do Hess's law. I might be able to use formation numbers. So the formation formula, formation of products minus formation of reactants, that's good. I can't use combustion. It's not ionic, so I'm not going to use Born-Haber or dissolution. So really, out of the 7 methods, I only have this one method. We spent most of the chapter talking about entropy, enthalpy. That was that one formula. Entropy from yesterday's lesson was also one formula. We talked about entropies being absolute numbers. There's an absolute perfect ordered for every crystal. This one here is just simply products minus reactants. Nicely, they've done for you here. Both of these guys here can be found on table number 12. So let me see if I can zoom in here so that I can save a little bit of space. Okay. So the enthalpy change is going to write over here. In my reaction, I'm producing a compound C4H8. You're going to find on table number 12 where you're given these values here, there's actually 3 compounds that actually have this C4H8. The one that they want is they want the compound that's named but1ene. So you just look up that entry there. What I want to do here is I want to take 4 times, because I'm going products minus reactants, take the enthalpy of formation of this but1ene, C4H8. I'm going to add 6 times the formation value for oxygen. We know that to be 0. We minus off the 4 times the heat of formation value for CO2 plus 4 times the heat of formation for water. Again, emphasis here is because it is a reverse of combustion, it is a liquid. So please double check my numbers here. But1ene as a gas, looking at the right column as well. So this is the 4th column over. This one here is positive 0.10. Enthalpy of an element, formation of element 0. The formation of CO2 as a gas, I'm getting negative 393.5. And for water as a liquid, so it's just called water, negative 285.8. Those ones there I know are quoted. First thing, the units are kilojoules per mole. So especially because I have some balancing in the coefficients here, I need to scale out the one that I know for 4 moles, and I want to just punch that through. So basically I'm going to take 0.10, I'm going to add 4 times 393.5, and then I'm going to minus the negative, so add 4 times 285.8, and I'm getting here the delta H is positive 2717.3. Again, your sig figs here, the least decimal place is 1 decimal place, so I can leave it 1 decimal place. The units are going to be kilojoules per mole. Again, do double check my numbers. They will always ask you this question here. All right, you just calculated delta H. What does it mean if delta H is positive? Well, if the energy change is positive, it means my reactants has gained energy. I end up at a higher energy state. In this case here, that being positive means endo. So as written, it's actually saying I don't really want to go that way because the other side is going to be less stable. It's going to be in higher energy state. But let's factor in the entropy argument as well. Let's see what that half of the story has to say. So in a similar manner here, we did this in our sort of mini lesson yesterday. So all we're going to do is we're going to take entropy of the butanene. There's an absolute entropy, so it's not a delta symbol here. I'm going to add 6 times the entropy, 6 times the absolute entropy of oxygen, minus off 4 times the entropy of CO2, and then add 4 times the entropy of water as a liquid again. Same table, but you're going to look at the very last column over. Again, double check my numbers here. But1ene, I get positive 306. 6 times entropy of oxygen has to be given to you, so that was given in the problem. Given the oxygen, we used that last day. So this one here is going to be 205 joule per Kelvin mole. The entropy change for CO2 is positive 213.8, so 4 times that value, and then 4 times the water, again as a liquid, so this is going to be positive 70. Again, do double check my numbers, make sure you're looking at table number 12, and what we're getting here, get that clearer here, 306 plus 6 times 205 minus 4 times 213.8, and then I'm going to minus off 4 times 70, I get the entropy being 400, also coincidentally positive. Just because the enthalpy positive doesn't mean entropy necessarily has to be positive. I just work through the numbers as they give me. What does it mean if the delta S, the change in entropy, as reactants become products, I actually gain entropy? This time, don't say endo, because we're not talking about energy anymore. This time, we're talking about the chaos. The amount of chaos increases, so it becomes more chaotic, it becomes more messy. That's actually the side I want to go to. Careful when you actually look at the units though, entropy is only measured in joule per Kelvin mole. It does have a little bit of energy dependence, but it's way smaller than the kilojoules. It's not even in the thousands, let alone the units. It's not even kilojoules. Now I have a competition. So based on the reaction as written, my energy level diagram says I want to stay on this side because this side here is more stable. I don't really want to go to the other side. However, my entropy argument says, well, because my most random phase here is 4 gas on this side, on the other side, in total, I have 7 moles of gas. The other gas side actually has 7 moles. I can make more of a mess because the universe tends to get more chaotic and more messy. I would tend to prefer to go to the other side. In this situation, there's some compromise, right? I want to stay on the left to be stable, but I want to go on the other side to be chaotic. We're going to figure out at this standard temperature, because I'm at this naught, which is 298, I'm going to figure out based on this delta H, delta S, depending on my temperature, does the enthalpy term win or does the entropy term win? So let's try it out here. The delta G is equal to, this change in Gibbs free energy, this new constant that we had, is equal to the positive 2713.7.3. I don't really want to go to the other side. Careful, this one here, I'm going to emphasize this is in kilojoules. I'm going to minus off the temperature. Oh no, they didn't give me a temperature. Well, because I know it's standard state, the standard temperature here is 298 Kelvin. Make sure you put that in your absolute scale. So 298 Kelvin, and then what we're going to do is we're going to multiply in the delta S. Don't multiply it in as 400, because this one here is only in joules. I'm going to actually write that as 0.4008 kilojoules per Kelvin mole. Because I want to do a subtraction later on, I want to make sure the units line up. So make sure you divide that by 1,000, so 0.4008. That's going to be joule per Kelvin mole. The kelvins cancel out. I'm going to show you the one middle step here. This first term here hasn't changed. The other one, because entropy is so tiny, in the formula it gets helped out by temperature. That's why it has more of a say on the reaction. Multiply it by the 0.4008. After adding together, this one here is still 119. When you crunch through the math there, 2717.3 minus this answer. If you can keep all the numbers, you can calculate it even better. So I'm getting roughly here, the free energy change is 2598. The units are going to be kilojoules per mole. This one here, they can ask you one last time, what does this delta G being positive mean? The positive delta H meant endo. Positive delta S meant more chaotic. A positive for free energy, this was the guy that I wanted to see. Less than 0 meant spontaneous. This time the delta G is positive, so delta G positive actually implies that it's non-spontaneous. Even though there is this toss-up, there is this sort of crossover value, I want to stay on this side, more stable, I want to go to the other side, more chaotic. I am not at a hot enough temperature for the entropy term here to be big enough to win out enthalpy. So overall, the delta G is very, very positive. The energy argument wins out in this case, and I'm going to say here, well, I'm going to stay on this side, this is non-spontaneous, which shouldn't really surprise you because I wrote this out as a reverse of a combustion. I expect a combustion to go 100%. I expect that to happen spontaneously. It's not natural for these particles to just up and recombine and become the butyene again. So I want to analyze this a little bit more here. That's basically the idea where we'll carry on through this lesson. We're going to examine the conditions that affect this delta G. We see that by formula, the delta G, I'm going to leave a little bit of room here because I do want to still do this derivation with heat of formation. So maybe I'll do it on this side here. So on the formula here, I know that the delta G is related to delta H minus T delta S. We had that formula. Depending on the sign, right, I just need to know the sign of this delta G. Positive is non-spontaneous, negative is spontaneous. What I can do is I can actually look at the combinations. What can the enthalpy be, X or endo? What can the chaos be, disorderly or not disorderly? I can look up the signs and I can figure out what combinations are possible for the sign of delta G. So here's what I mean. What if we had another reaction, and what if it was written as we go from reactions to products? What if it was exothermic? What if the delta H was negative? Let's say when we go from those reactions to products as written, we also get more chaotic or chaotic. This one here is more disorderly, this is positive. What are the possibilities of the sign if delta H is negative and I want to become more chaotic? Absolute temperature is always going to be positive. Delta S here is going to be positive. What are my possible signs out of that math there? In that case, you should be able to see, well, I had a negative number. I might have something positive. The only thing for me is delta G is going to be negative. If delta G is negative, I can then say spontaneous. So in that case here, that combination, negative is exo, entropy is positive, it's going to be spontaneous at every temperature. What if the reverse was true? What if, as written, the reaction was endothermic? I don't really want to go to the other side because it's higher energy, it's less stable than me. And what if the other side is also more orderly? What if my amount of chaos, my amount of disorder actually decreases? You don't need to memorize this here. It's easy enough just to look at the signs here. If delta H here is positive, I'm going to minus off, again, temperature is always going to be positive, so that doesn't affect anything. But delta S is also negative. If I take a positive and a minus a negative, my only choice for delta G is always going to be positive. These are, regardless of temperature, always going to be non-spontaneous. If my energy argument says, nope, the other side is less stable than me, and the other side, entropy, says, oh, I'm actually more disordered on this side, I don't want to become more ordered, regardless of temperature, those are always going to be non-spontaneous. In a case like we just did, however, even though it was a lot of work, we had to find the enthalpy first, we had to find the entropy afterwards, and then recombine it. We had a sort of toss-up. We actually had case number 4. We had an endothermic as written, so I really don't want to go to the other side, so I'm going delta G equals delta H minus T delta S. I don't want to go to the other side, but the other side had 7 moles of gas, the other side was more chaotic. This time, more chaotic here meant positive. When those changes are going to be the same sign, I'm going to have a positive minus temperature and positive. This time I can get two things. This time, when my temperature is tiny, at low temperatures, the entropy term really can't win out. So I take a positive, big positive minus a small positive number here. The delta G here is still positive, and if delta G is positive, it's non-spontaneous. However, because there is this compromise, because I do have this natural tendency to want to become more messy, if I heat up the temperature, if I make it hot enough, that this positive change in entropy actually gets bigger. Not that the delta S itself changes. We're going to make the assumption that as you change temperature, the delta H and delta S don't change. But if I'm hotter, if I'm actually more than the 298 from earlier, if I take a small positive minus a big positive enough, at a really high temperature, temperature wins out, the delta G is actually less than 0, and then therefore I'm going to be spontaneous. This actually introduces another style of question they can ask you. They're always interested in which feature is making you spontaneous. In this toss-up, the only reason why delta G could have been negative is if the entropy term wins out. You can say in this argument here, you can say entropy drives the spontaneity. Again, the entropy here, that number won't change, but if the temperature is hot enough and this T delta S term becomes large enough, that term can overall win out over the enthalpy argument. We have the other crossover case here, also temperature dependent. This time it's exothermic overall, but it's becoming more ordered. I'm also having the same sign. When I go delta G, delta H minus T delta S, I have the delta H already negative. That could potentially already put delta G to be negative, but what I'm going to do is I'm going to be minusing something that's also negative. In that case, there's similarly, if I have a low temperature, if this term here is not very important, I take a negative number like negative 100, I then add like 20 to it. I'm still overall negative. This time at low temperature, we're spontaneous, and we can actually say the spontaneity decreases as temperature increases. So also temperature dependent, but you notice it's in reverse. Earlier, low temperature was non-spontaneous. For this combination, low temperature is actually spontaneous. You don't need to memorize any of that because you can just, we know the formula from section 1, and you basically, if you're given enthalpy, if you're given entropy, just figure out what happens to the signs. Especially if you're given the numbers, you can actually calculate the numerical value, and based on that numerical value, you can actually figure out, are we overall spontaneous or not. It was a lot of work to actually find this delta G. So what we do on the top of the backside, we're going to introduce a guy here called Gibbs free energy of formation. The of formation part is exactly the same. Standard state, everything is just the same. You're going to have that pesky 1 mole. You're going to be forming it from the constituent elements. Everything is the same. The only difference is this time it's not enthalpy change. This time we're looking at the free energy change. So on table number 12, they actually give you one middle column. We've used the 4th column for delta H's. We've used the 6th column over for entropy. There is a column in the middle that actually gives you Gibbs free energy of formations. And what's going to happen is if you have the Gibbs free energy of formations, again, formation of any element is 0. There's no reaction for that. You can also go products minus reactants. So if you can take a second, go back to our earlier question. We have our numbers. It was a lot of work trying to find delta H separately, delta S separately, and then combine them afterwards. What if I just use this formula to find the overall Gibbs of reaction? You take the Gibbs formation of products minus the Gibbs formation of reactants. This will give you a nice shortcut here. I'm going to show you what I'm typing in. So I'm going to take the relative Gibbs formation of your products here are but1-ene, C4H8. I'm going to add 6 times the value Gibbs formation of oxygen. That's going to be 0 because I can't form any elements from anything simpler. I minus off 4 times the Gibbs of CO2, and then I'm going to add 4 times the Gibbs of water, again as a liquid. So again, you can find these on table number 12 on the 5th column over. So again, double check my numbers for me here. But1-ene, I'm getting positive 71. This one here is 0, like we said. For CO2, the Gibbs is negative 394.4. And then for water as a liquid, this one here is negative 237.1. All of them in kilojoules per mole. So we're going to go 71, add a 4 times 394.4, and go to add 4 times 237.1. No real surprise here. This is giving us roughly the same number, positive 2597. The units are kilojoules per mole, and you see that's quite a bit of a shortcut here. I didn't need to do enthalpy first, then do entropy, then put it together. I right away know, as reactants become products, here's how much your free energy itself actually changes. What we can argue for now is because this here is positive, positive then implies this one here is a non-spontaneous reaction. You will have to be able to do both, even though this one here is a nice shortcut. The reason why is, especially for a combination where temperature is actually going to be dependent, there's no way of actually setting at what temperature do we switch over from spontaneous or non-spontaneous. You have to know what's the energy argument, what's the entropy argument for that exact question for you to actually mix and match them to get the delta G. Last little bit here. So we're going to try to figure out what's the significance of the number of delta G. So the sign, so far we said if delta G is less than 0, we know it's spontaneous. When delta G is bigger than 0, we know it's non-spontaneous. The crossover value is actually going to be 0. What's the importance of the size of the number? Basically, spontaneous, we've been assuming a spontaneous reaction goes 100%. As written, reactants just fully become products. On non-spontaneous, we've been assuming that this thing here goes 0%. Our reactants just simply don't want to become products. It's because products are going to 100% backwards going to become reactants. Again, this flip doesn't occur all at once. What we're going to actually do, this is just an experimental value. Many reactions actually don't go to completion. They instead reach a guy called equilibrium. They have some sort of compromise between the two of them. They don't go fully, or they don't go no reaction. Next year, we're going to introduce this more as an equilibrium constant. It's a ratio K that measures sort of products over reactants. Basically, experimentally, they said, all right, I know negative means spontaneous. I know positive means non-spontaneous, but I'm going to give myself a little bit of room. If my free energy change is anywhere between negative 30 and 30, let's say anything more negative than 30, these are going to be 100%. Anything that's bigger, more positive than 30, these are going to be 0%. But what if the delta G was, let's say, negative 20 or negative 10? That's when I'm going to actually start crossing over, well, maybe I only get 90% of the way or 80% of the way. It takes a little while. These would be situations called equilibrium. Basically, the reaction can go forwards or reverse. We're going to hit some balance in between. If the reaction goes 60%, do we say spontaneous or not? Well, it kind of goes forward. Maybe it's leaning forward, but there is a little bit of crossover. That's what's actually indicated by the magnitude of this number. So if you want to just read through this table here, the 30 is just a rough ballpark number. Anything beyond on either side, more positive than 30, more negative than negative 30, those are pretty even, but it does switch over between 30 and negative 30. The diagram that I just want to introduce to you here, this one here gets a little bit confusing. So we're going to do, if it wasn't confusing enough, I'm just going to zoom in on this one diagram here. What they're plotting for you here is they're actually plotting the actual Gibbs free energy. They're not plotting the change in free energy. They're plotting all the energy that's available from the battery. We do still have the reaction axis on this side, so it's reactants becoming products. Let's say our delta G here is a very large negative number. Earlier it was positive. Let me just make up a number. Let's say our delta G value. Let's do a reaction where delta G is equal to negative 100. All right, so very far away from this boundary value. So negative 100, it's negative, so we know it's spontaneous. We know it pretty much goes 100%. What we're actually saying is we're saying, well, the reactants do 100% want to become products. We started off our battery with a lot of free energy, a lot of electrical energy available. Over the course of the reaction, as you go from reactants to products, this Gibbs free energy value here actually drops. It actually gets lower. So it actually becomes this lower value here. What's going to happen here is because there's a relationship between G and this K value, this equilibrium constant, as this delta G value here, this delta G, this change is negative 100. As it gets more and more negative, as we drop by more, the curve actually ends up pushing over. So what's going to happen is delta G negative, delta G negative is always going to be spontaneous. I can be delta G negative. I started off way up here. The delta G is negative for me to actually fall down this curve here. Mixtures are always going to be more chaotic than the pure substances. So what's going to happen here is the mixture actually represents something we call equilibrium. The part that we end up with, the mixture that's going to be at equilibrium is going to be very close to the product side. So mixture lies close to products. And in that case there, because it's close to products, we can conclude this is going to be 100%. It's a completion reaction. It just goes all the way. In fact, going from pure products to have the odd reactant around here, that also is a delta G negative. It's also spontaneous. But because this bottom point here, this lowest free energy point here, is so close to the product side, pretty much we're 100% reaction. What if I was actually a positive number? So what if I was like starting off with low free energy, in the end I get high free energy, so reactants and products. This time, numerically, my delta G is positive. Let's do a delta G of, I don't know, positive 50. So if I win by 50, The curve here, again, is going to fall on both sides, but because of this being really positive, the curve is going to be really heavily slanted, like I've shown you here. The mixture that we end up with, as we fall towards that low free energy point here, the mixture is pretty much only going to be 0%, so pretty much we can say no reaction. You can then imagine with me here, that was beyond the, sorry, I was 100, the other one was about 50. What if I was about 30? If I'm about 30, the difference, the drop between the top and bottom is not as dramatic. This curve here may not necessarily be all the way over one side, all the way over the other side. Maybe we have a curve something like, maybe my delta G goes from, I can do a value here, negative 20, maybe it only drops to become, I don't know, negative 30. So delta G is final minus initial. The delta G value here is negative 10. The negative does tell me overall spontaneous, but what you're going to see here is from this curve, you're going to see that the equilibrium that we end up with is actually somewhere in between. We're not necessarily spontaneous like 100%. We're not necessarily non-spontaneous like 0%, but we're somewhere in between. Maybe we're 60% of the way. So overall, you can still classify me as spontaneous, but because the size of it is not that big, I can imagine that we're in some equilibrium, we're some middle value over. You'll notice here I actually introduced one last element here. Although free energy is the amount of energy that's available for use, usually we define zero potential energy as when charges are infinitely far away. That's the zero case, so all the other energies are going to be negative. What we're carrying is our battery starts off with a smaller negative number, like negative 20, and we drop to something like negative 30. That means I have 10 kilojoules of free energy available for use. When we become a dead battery, the reactants and the products will be exactly matched up. There's going to be a perfect equilibrium. I would have a dead battery. It wouldn't work anymore. One other way to think about free energy here, delta G is equal to delta H minus T delta S. The delta G was supposed to be my free energy. This is how much energy I have access to, I can utilize. In this case here, the energy term was supposed to be all from enthalpy. So let's use a money argument here. Let's say you have $1 million. You were supposed to be able to use all the $1 million. But because entropy itself also has energy dependence, but that energy here represents energy that's locked away, it's sort of like when you buy a house, right? Maybe in the future, you may need to put down a down payment. I have $1 million. I was supposed to be able to utilize all $1 million, but then because I need to pay my mortgage, I need to put down a down payment. Maybe I put down, I don't know, $400,000. I've locked that away into my house. So out of the $1 million, I minus the $400,000. I now have $600,000 that's still freely available for me to use. I can go to McDonald's. I can use that money. I cannot take a chip of my wall and be like, hey, this cement here from my house is actually worth such and such amount. They won't take that, because even though it is your money, even though out of my examples was I have $1 million, even though the $400,000 is still your money, that money there is locked away. It's no longer available for you to use. After the subtraction, it gives you the leftover $600,000 that's available for you to use, which is why it's called free energy. It gets a little bit sloppy because it has to be negatives as well, but overall we're just looking at changes. If we go from a sort of closer to zero negative number like negative 20, if I drop to negative 30, I still have a positive 10 kilojoules of free energy that the battery can provide. So with that, I'm going to leave you with this last question here. Should be a fairly simple question. They give you an equation like this. They give you all the thermodynamic data. Usually you would have had to look for table number 12, but in this case here, I've given you all the values. I'm asking you to do it both ways. I'm asking you to find delta G using Gibbs free energy formation. So utilize these values, again, as products minus reactants. I'm asking you to do it the first way as well. Find the enthalpy and find the entropy separately. You'll notice the wording of this last question here. Find the minimum temperature. Find the special temperature. Notice the wording here says, when does the reaction above which the reaction becomes spontaneous? That implies to me that these two answers that you get here, you should find that currently we're non-spontaneous. The only way you can find when it crosses over is when delta G, so delta G less than 0 was spontaneous. Delta G bigger than 0 was non-spontaneous. When it crosses over, what's that special temperature, is setting the delta G actually equal to 0. So delta G, which is supposed to be delta H minus T delta S, we're no longer going to be 298 like we've been doing for standard state, like we've been doing for this not symbol here. If I let T be a variable, but this time I let this equal to 0. Notice you can only do this method if you did it brute force. If you did both the delta H and delta S, you can find the temperature. You can isolate the terms here. The temperature would be what's your enthalpy change and what's your entropy change. Careful, this is going to come out as a Kelvin temperature. If they ask you overall final answer in Celsius, you just convert it back to Celsius. So just let me summarize for you as you just practice your way through. There are 2 different ways of finding delta G. The first way here is using the formation values. It's nice and quick. It gives you whether we're positive or negative. It tells me right away where it's non-spontaneous. The second equation here, you also need to know, it requires you to do enthalpy first, then entropy. It allows you to put them together also to find the same delta G we found earlier, but the second method here has the advantage. It then leaves this T term out, so you can actually solve for, especially when you have that crossover case here, at what temperature do we switch from spontaneous to non-spontaneous and vice versa. So try out that one question there. I'll give you a worksheet that you can practice some more. And that's the end of our new stuff. So we'll just switch over into review mode and we'll go from there. Thanks, guys. Take care.